Before there were telescopes, before glass and brass and the whisper of polished mirrors touched starlight, humanity lifted its eyes to the night sky and wondered whether that black canopy had a border. The first shepherds, who marked the seasons by the slow migration of constellations, saw the sky as a roof, domed above the world like the ceiling of a vast hall. In Mesopotamia, where cuneiform tablets pressed wet clay into the first written reflections of cosmic order, the heavens were imagined as layers, transparent shells of lapis lazuli, each carrying divine lights fixed upon them by invisible hands. The world, to those ancient minds, was not infinite, but carefully enclosed, as if reality itself had been hammered into a vessel and sealed by the gods. From the floodplains of the Nile, Egyptian priests traced the daily voyage of Ra's solar bark, believing the sun god passed beneath the horizon each evening through an unseen gate into the underworld, only to rise again, reborn, through the eastern portal of dawn. The edges of space were mythic thresholds, guarded by serpents and stars. Across the Mediterranean, the Greeks inherited these celestial questions and reshaped them into geometry. When Anaximander spoke of the apeiron, the boundless, he did not describe infinity as we might today, but a primordial expanse, undefined and eternal, out of which all worlds arise and return. His cosmos was not enclosed by walls, but suspended in the limitless, and yet that very limitlessness frightened thinkers who sought harmony, proportion, and structure. Pythagoras, whose music of the spheres would echo through centuries, imagined concentric crystal orbs, each turning with mathematical grace. In his universe, order reigned supreme. There could be no chaos at the margins, for each boundary was part of divine symmetry. But then came Democritus, the laughing philosopher of Abdera, who dared to say that space itself was infinite, a vast void filled with countless atoms colliding in endless dance. To him, the universe had no center, no edge, no favored place. Every world, every sun, every creature was a temporary pattern in the infinite sea of motion. This thought, scandalous and sublime, would sleep for 2,000 years before science learned to breathe its air again. When Aristotle rose to authority, he restored the boundary. The heavens, he said, were perfect, immutable spheres surrounding the corruptible earth. Beyond the sphere of fixed stars lay the prime mover, the pure actuality that set all things into motion. The cosmos was finite, closed, and complete, a celestial architecture so harmonious that even medieval theologians would later find divine comfort in its walls. And yet, even within that perfection, in Alexandria, the mathematician Eratosthenes measured the Earth's circumference with shadows and sticks, hinting that human intellect could stretch its hand beyond myth. Claudius Ptolemy, in his Alchemist, built a model so intricate that it imprisoned the cosmos within gears of epicycles, deference, and equants, a clockwork sky centered on Earth. For centuries, this geocentric cage would endure, its mathematical precision hiding its philosophical fragility. Then, across the quiet plains of Poland, a canon named Nicholas Copernicus lifted his gaze and reversed the gears. The sun, not the earth, was the center. The spheres rearranged. The universe expanded, not yet to infinity, but to a scale that bent human imagination. When Giordano Bruno read Copernicus, he saw not a new order, but a liberation. He declared that the stars were other suns, each with their own worlds, each world perhaps with its own inhabitants. To Bruno, space had no edge, no enclosing sphere, no center at all. He called it the infinite field of God.
For this, he was burned at the stake in 1600, his eyes reflecting the infinite he had dared to name. Yet his ashes scattered into the very air he had described, and in them a seed took root. In the next century, Galileo Galilei raised his telescope toward the sky and shattered Aristotle's crystal spheres. The moon had mountains, the sun had spots, Jupiter had moons of its own. The heavens were not immutable, they were dynamic, imperfect, alive. With each observation, the boundaries of space receded a little further, as if reality itself were being forced to confess that it had no end. Isaac Newton, in his Principia, gave the universe its first great mathematical skeleton, a cosmos bound by gravity but without walls. His space was infinite, absolute, and uniform, a stage upon which celestial bodies danced forever. Yet even Newton felt the weight of infinity's paradox. If the stars filled an endless void, why was the night not ablaze with their light? That question, the darkness of the night sky, would echo through generations, whispering its riddle into every telescope. When Edmund Halley charted the comet that bears his name, he thought in orbits, not edges. The more astronomers mapped, the larger the cosmic chart became. In 1755, Immanuel Kant, the philosopher who dissected reason itself, wrote Universal Natural History and Theory of the Heavens, proposing that our Milky Way was but one island universe among countless others drifting in an immeasurable ocean. He used the word infinite with a kind of reverent caution, aware that it was less a number than an abyss of thought. And yet, through Kant's pen, the human mind stretched further than any lens could see. William Herschel, in the late 18th century, turned his enormous telescopes upon the sky and began to count the stars. He and his sister Caroline spent night after night sweeping the heavens, mapping nebulas, discovering Uranus, and sketching the Milky Way's shape. They believed they were measuring the limits of the universe, yet what they truly measured was the limit of their own instruments. The faint smudges they cataloged, those ghostly patches of unresolved light, would later prove to be galaxies beyond number. Herschel's maps, exquisite.
Then, in 1917, Albert Einstein bent space itself. His general theory of relativity transformed the cosmic stage into a living fabric, curved by matter and energy. In this new geometry, the universe could be finite yet unbounded, like the surface of a sphere that has no edge but still encloses volume. For the first time since Anaximander, science returned to the idea that infinity might be unnecessary to abolish boundaries. Einstein, however, feared instability. He introduced the cosmological constant to keep his universe static. But in doing so, he unintentionally laid the seed for cosmic expansion. When Edwin Hubble aimed the 100-inch Hooker telescope toward Andromeda in the 1920s, he discovered that the faint nebula was not part of our Milky Way, but a galaxy of its own, separated by millions of light years. Space did not merely contain stars, it contained entire universes of stars. And when Hubble measured their redshifts, he saw that every distant galaxy was receding, the further, the faster. Space was not a stage, it was a swelling ocean. The universe was expanding, and the question of its end became a question of time as much as of distance. The 20th century became the age of cosmic revelation. Georges Lemaitre, a Belgian priest and physicist, proposed that the universe had once been condensed into a single primeval atom, a beginning from which all expansion flowed. In 1965, Arno Penzias and Robert Wilson discovered the faint hiss of the cosmic microwave background, the afterglow of that birth. The universe was not eternal in its current form. It had evolved, expanded, cooled. Space itself had a history, and that history stretched backward not to infinity, but to a singular beginning. And still, beyond the horizon of observation, its future reached towards something no one could yet define. As the decades advanced, cosmologists built models, open, closed, flat, each describing how the universe might behave. The density of matter and energy would decide whether expansion would slow, halt, or reverse. A closed universe would eventually collapse in a big crunch. An open one would expand forever into silence. A flat one would balance perfectly between the two, stretching endlessly without end or boundary. Measurements of the cosmic background radiation, especially from the COBE and WEMAP satellites, refined the parameters. The result was astonishing. The universe appeared almost perfectly flat. Space, as far as we could measure, extended without curvature, without edge. But there was more. In 1998, two teams of astronomers observing distant supernovae found that the universe's expansion was accelerating. Instead of slowing down under gravity, galaxies were flying apart faster and faster. Something unseen, dubbed dark energy, was driving this cosmic acceleration. Einstein's abandoned cosmological constant returned now, transformed from a mathematical convenience into a mysterious force filling the vacuum. If this energy remained constant, the universe would not end in collapse, but in a cold, eternal stretching, the so-called heat death, where stars burn out and
Meanwhile, astronomers mapped the cosmic web, a lattice of galaxies and dark matter stretching hundreds of millions of light-years across. Supercomputers simulated its filaments, its voids, its silent expanses. The scale defied comprehension. Between the clusters lay regions so vast and empty that entire galaxies could drift through them unseen for eternity. And yet even these voids are not outside space. They are space itself, thinned to its cosmic bones. The more we map, the clearer it becomes. The universe has structure, but no border. At the frontier of theory, physicists like Roger Penrose, Stephen Hawking, and later André Linde tried to peer beyond the Big Bang. Penrose's conformal cyclic cosmology imagined that before our universe there was another, its final radiation stretching into ours as the faintest trace in the microwave sky. Hawking proposed that the universe might be finite, yet without boundary, like the surface of a sphere extended into 4 dimensions of space-time. Linde's eternal inflation suggested that new universes constantly bud off from the quantum vacuum, each with its own laws of physics. In these visions, end dissolves entirely into transformation. But the question persists, as stubborn as starlight. If the universe has no edge, what lies beyond its observable horizon? We cannot see it, but the equations tell us it must exist. Regions where the galaxies are so far away that their light will never reach us. The observable universe, about 93 billion light-years across, is merely a shrinking island in an ocean whose shores recede faster than light itself. To stand beneath the night sky today is to look not outward, but backward in time, each photon a messenger from an era when the cosmos was younger, denser, smaller. The further we gaze, the closer we approach the dawn of space itself. And yet within that gaze, the human story unfolds, our endless attempt to frame the infinite. From the ziggurats of Babylon to the detectors buried beneath Antarctic ice, every generation builds instruments to measure what may be immeasurable. The James Webb Space Telescope, stationed beyond the moon's shadow, peers into galaxies whose light left them before the Earth existed. Its mirrors catch not the boundary of space, but the earliest flicker of stars igniting from primordial gas. Each new image, each data stream extends the line of human vision further into the unknown, but never to an edge, only to another question. The story of our search for the universe's limits became, over centuries, a chronicle of expanding ignorance as much as expanding knowledge. The more precisely we measured, the less certain we became of what space truly was. In the early 20th century, while Einstein was bending geometry to the mass of the stars, mathematicians like Felix Klein and Henri Poincaré were exploring non-Euclidean spaces where parallel lines could meet and triangles could sum to more or less than 180 degrees. What once seemed abstract speculation soon found itself carved into the very substance of reality. The cosmos, it turned out, could possess curvature without walls, topology without edges, volume without a beyond. When the Russian mathematician Alexander Friedmann applied Einstein's equations to the whole universe, he discovered that static space was impossible. It must expand or contract. The eternal firmament.
That realization was both scientific and existential. Humanity had long imagined itself as a fixed point within a cosmic hierarchy, but now even the hierarchy itself was in motion. Hubble's galaxies became living actors in a universal expansion. Space was stretching, carrying the galaxies with it, not as projectiles through a void, but as raisins in rising dough. And in that expansion, time itself became a participant. Every clock in the cosmos ticked differently, each according to its path through space-time's curvature. The Newtonian backdrop dissolved. There was no outside of space to ask about, no frame beyond the universe. The question, does space end, became almost linguistic, tangled between human intuition and mathematical revelation. By the mid-20th century, the notion of a finite yet unbounded universe gained philosophical traction. George Gamow and his collaborators Ralph Alpher and Robert Herman calculated the temperature of the leftover radiation from the Big Bang, long before anyone had the instruments to detect it. Their prediction, dismissed for years, would become the smoking gun of modern cosmology. When Penzias and Wilson's radio antenna in New Jersey accidentally caught that faint uniform hiss, they thought it was pigeon droppings on the equipment. It was, in fact, the echo of creation. Space itself was not eternal. It had once been compressed into a state of unimaginable density, smaller than an atom, hotter than any furnace, and then it had exploded, not into pre-existing emptiness, but into itself. Every point in the universe expanded away from every other point. There was no center, there was no edge, there was only expansion. With this understanding came a new sense of cosmic geography. Astronomers began to speak of the cosmic horizon, the maximum distance light could have traveled since the beginning of time. Beyond that, no information could reach us, not because something prevented it, but because space-time itself was stretching faster than light could cross it. The observable universe, a sphere centered on every observer, became a personal cosmos, finite in sight, but potentially infinite in extent. It was as if every conscious being stood at the center of its own private bubble of visibility, surrounded by unseeable infinity. Yet even infinity, once a philosophical abstraction, began to take on mathematical flesh. Inflation theory, developed in the 1980s by Alan Guth, André Linde, and others, transformed the Big Bang into something far more dramatic. In its earliest fraction of a second, the universe underwent an exponential expansion, space doubling in size countless times in less than the blink of an eye. Quantum fluctuations, magnified by this inflation, became the seeds of galaxies, the fingerprints of randomness frozen into the sky. Inflation not only explained the uniformity of the cosmic microwave background, but also hinted that our entire visible universe might be just a small patch of a vastly larger multiverse. If inflation never stops, but continues in different regions, spawning new universes endlessly, then the question of whether space ends dissolves entirely. Each end births another beginning. Infinity becomes not a distant horizon, but a process.
At the same time, theoretical physicists turned inward, probing the fabric of space at the smallest scales. Quantum mechanics, the science of uncertainty, revealed that even the emptiest vacuum teems with energy. Virtual particles flicker in and out of existence, borrowing reality from nothing and repaying it in an instant. Space is not a tranquil void, but a restless sea of potential. When combined with relativity, this quantum chaos suggests that space-time itself might be granular, woven from tiny loops or strings vibrating in higher dimensions. The string theorists, in their intricate mathematics, speak of brains, multi-dimensional membranes that could collide, creating new universes in the process. In such a picture, our cosmos might be a three-dimensional sheet adrift in a higher dimensional ocean. The end of space could merely be the boundary of our brain, invisible to us but adjacent to others, like pages pressed together in a cosmic book whose binding we cannot see. Meanwhile, astronomers built their instruments larger, colder, and more precise. Radio telescopes stretched across deserts. Space observatories orbited beyond the Earth's interference. The Sloan Digital Sky Survey mapped millions of galaxies, revealing a universe patterned like foam, vast filaments of matter surrounding enormous voids. The large-scale structure looked less like the orderly heavens of Ptolemy and more like the nervous system of a living mind. In every direction, the same pattern emerged, fractal in spirit, if not in mathematics. The more we looked, the less we found any sign of an edge. Even the voids, the great cosmic deserts, were not gaps between universes, but hollows within the same continuous space. This realization struck at something profound within the human psyche. For millennia, end had meant safety, enclosure, definition. To discover that we live in a universe without end was to confront a kind of existential vertigo. Yet the philosophers and poets had always sensed it. Lucretius, in his On the Nature of Things, had imagined throwing a spear at the edge of the cosmos. If it flies onward, there is no boundary. If it strikes something, then that barrier must itself have another side. Centuries later, Pascal would confess that the eternal silence of these infinite spaces frightens me. But to the physicist, infinity is not frightening. It is a boundary condition, a mathematical convenience. Between the terror of the poet and the calculus of the scientist lies the fragile wonder of being a finite creature in a limitless stage. In the 1960s and 70s, radio astronomy began to probe the depths with unprecedented sensitivity. Quasars, quasi-stellar radio sources, appeared as brilliant beacons at the edge of the observable universe, powered by supermassive black holes devouring matter at the hearts of young galaxies. Their redshifts pushed our horizons further still, showing that light could traverse billions of years before arriving at our instruments. These were not the edges of space, but echoes of its youth, fossilized in photons. The universe had no periphery, only a past.
Black holes, once thought theoretical curiosities, became the laboratories of the ultimate questions. In their gravitational abyss, space and time fold upon themselves, creating regions where our equations break down. The singularity at a black hole's core
where density and curvature become infinite, mirrors in miniature the singularity of the Big Bang. Does space end inside a black hole, or does it continue invisibly into another domain? Some physicists speculate that black holes might be gateways to other universes, their interiors ballooning into new expansions. Others argue that quantum gravity will eventually remove the singularity, replacing it with something finite yet still mysterious. The truth remains hidden behind the event horizon, that perfect boundary where even light cannot escape, but where space, paradoxically, may continue. As theories multiplied, so too did technologies. The cosmic background explorer, COBE, in the 1990s, confirmed the faint ripples in the microwave background, fingerprints of those primordial quantum fluctuations. The Wilkinson Microwave Anisotropy Probe, WMAP, refined the map, and later the Planck satellite traced it with exquisite precision. The data whispered a consistent message: space is flat to within a fraction of a percent. In a flat universe, parallel lines never meet, and geometry extends forever. Yet flat does not mean simple. The topology of the universe could still be finite if it loops back on itself in complex ways, like a higher dimensional torus, where traveling in one direction long enough brings you back to your starting point without crossing an edge. Some cosmologists have searched for matching circles in the cosmic microwave background, signs that light has wrapped around the cosmos. None have been found, but the possibility remains mathematically alive. Meanwhile, the mystery of dark matter deepened. Invisible yet gravitationally essential, it forms the scaffolding upon which galaxies and clusters coalesce. Its nature remains elusive, perhaps weakly interacting particles, perhaps primordial black holes, perhaps something stranger still. Without dark matter, the visible universe would lack cohesion. Stars would drift apart, galaxies would unravel. With it, space itself gains structure, a skeleton beneath the luminous skin. The search for what fills that skeleton became the next great frontier. And beyond even that, the enigma of dark energy, smooth, omnipresent, and utterly dominant, defined the fate of all things. Together, dark matter and dark energy comprise about 95% of the cosmos, meaning that everything we can see, from stars to human bodies, constitutes the faintest fraction of reality.
Such ideas blurred the boundary between physics and philosophy. The question, does space end, became intertwined with what is real and what is information. Theorists like Juan Maldacena developed models of anti-de Sitter space where gravity in a bulk volume corresponds to quantum field theories on its boundary. Others wondered if our own universe, nearly flat and accelerating, could obey similar rules. If so, then the end of space might not be a physical wall, but a limit of correspondence, a surface where dimensions trade identities. Space would not end, it would transform. Even as theory spiraled into abstraction, observation pressed relentlessly onward. The Hubble Space Telescope, launched in 1990, began returning images of galaxies so distant that their light had left them when the first multicellular life was forming on Earth. The Hubble Deep Field, assembled from weeks of exposure aimed at an apparently empty patch of sky, revealed thousands of galaxies packed into a fragment the size of a grain of sand held at arm's length. Each speck was an island universe, each containing hundreds of billions of stars. The end of space receded again, not into philosophical infinity, but into lived astonishment.
For every image the telescope returned, the mind's horizon stretched a little further, and the night sky became a map without borders. Astronomy, once the domain of philosophers and priests, now became a collaborative enterprise of nations and generations. Giant observatories rose on Chilean mountaintops. Radio arrays sprawled across the plains of South Africa and Australia, and detectors like LIGO began to hear the universe instead of merely seeing it. Gravitational waves, ripples in space-time predicted by Einstein, were detected in 2015, confirming that even the geometry of existence can quiver and sing. Those waves came from colliding black holes over 1 billion light-years away, proving that space is not static, but alive with motion, stretching and compressing like the skin of a cosmic drum. Each vibration carries the story of matter's most violent dances, yet even these waves fade into the vastness, dispersing into an ocean with no shore. And as we listen to them, the question grows no quieter. If space can ripple, if it can stretch and bend, can it also end? The mathematics says no, at least not within the framework we know. But the human imagination insists on asking. Beyond the last galaxy visible to our telescopes, beyond the last photon that can ever reach us, something lies. Perhaps more space, perhaps another reality, perhaps nothing at all. The frontier between knowing and not knowing is itself the only true edge we have ever found. By the dawn of the 21st century, cosmology had become a symphony, played on instruments scattered across the planet and in orbit above it. Detectors in Antarctica listened for neutrinos gliding through the Earth like ghosts from distant supernovae. Satellites mapped microwaves left from the first fraction of a second after the Big Bang. Particle colliders near Geneva recreated miniature flashes of primordial fire, hoping to glimpse the laws that governed creation itself. In this immense collaboration of human will, the cosmos ceased to be a static backdrop and became a living field of experiment. Yet every discovery deepened the question: if the universe is expanding into nothing, what is that? Mathematics offered one answer after another, each as intricate as a cathedral and just as fragile. The topology of three manifolds, once the playground of pure geometry, entered physics through the work of Thurston and Perelman. Their insights showed that finite, boundaryless spaces could assume forms stranger than any sphere or torus, spaces that twist back on themselves in ways the imagination cannot picture. Cosmologists began to model universes shaped like dodecahedra, like Mobius ribbons, like multi-connected halls of mirrors where light might loop endlessly, producing multiple ghost images of the same galaxy. If such patterns exist, the night sky could contain reflections of itself, illusions born not of distance, but of geometry. To find them would be to glimpse the architecture of infinity. Meanwhile, observations of distant Type A1 supernovae continued, refining the measure of cosmic acceleration. The Hubble constant, once a single number, became a battleground of precision. Measurements from the early universe, encoded in the cosmic microwave background, disagreed subtly, yet persistently, with those from nearby galaxies. This Hubble tension, as it came to be known, hinted that something profound might be missing from our model of space. Perhaps dark energy evolves with time. Perhaps gravity behaves differently on cosmic scales. Perhaps the universe hides new dimensions that leak influence into ours. Each hypothesis stretched the definition of space further, like fabric pulled toward tearing. While telescopes looked outward, others looked inward, peering into the hearts of atoms and the depths of mathematics for signs of structure beneath the Planck length, the scale where space-time itself might dissolve into quantum foam. Loop quantum gravity proposed that space is woven from discrete loops of field, finite in number, yet vast in combination, eliminating infinities by quantizing geometry itself. In this vision, the universe is built from threads, not continuum. String theory, more ambitious still, replaced points with vibrating strings whose resonances generate all particles and forces. 10, 11, perhaps even 26 dimensions shimmer beneath the apparent 3, compactified into shapes known as Calabi-Yau manifolds, curled so tightly that only their effects can be felt. The end of space might lie hidden within those microscopic folds, unreachable but omnipresent, an inward infinity balancing the outward one. As computation grew, cosmologists built digital universes, simulations containing billions of particles of dark matter.
Human culture absorbed these revelations in its own way. Painters turned nebulae into icons of transcendence. Composers transcribed radio waves from pulsars into music. Poets reimagined infinity not as terror, but as belonging. The Renaissance had placed man at the center. Modernity had displaced him. The new cosmology invited him to dissolve entirely, a pattern among patterns. Yet paradoxically, the more we vanished in scale, the more intimately connected we became to the cosmos. Every atom in our bodies was forged in stars. Every photon that warms our skin has traveled across billions of kilometers of the same expanding space. To ask whether space ends is also to ask whether we ourselves end, or merely change form as the universe continues its unfolding. In laboratories cooled to near absolute zero, physicists created miniature analogs of the cosmos, Bose-Einstein condensates, where quantum fields could mimic the curvature of spacetime. Hawking radiation, once unobservable, began to appear in these artificial horizons. The boundary between experimental physics and metaphysical speculation blurred. If horizons could be simulated, could the universe itself be a kind of emergent phenomenon, a condensation of deeper laws? Some theorists, following the logic of emergence, propose that space and time arise from entanglement, the quantum linkage between particles. In their equations, geometry is nothing but the pattern of information sharing. Break those links, and space itself disintegrates. In that view, the end of space is not a wall, but the failure of connectivity, a place where correlation vanishes and reality loses coherence. Across continents, gravitational wave observatories multiplied, triangulating collisions of black holes and neutron stars. Each detection added a new verse to the cosmic song. One signal, GW 170817, carried both gravitational waves and light, allowing scientists to measure the expansion rate directly and to trace heavy element creation in the kilonova's aftermath. Gold, platinum, and uranium, substances of crowns and reactors, were revealed to be the ashes of colliding stars. Space, it seemed, was not a static expanse, but an alchemical furnace. The boundaries that once separated myth from measurement, poetry from physics, began to dissolve. Even so, doubt remained the universe's constant companion. Some cosmologists argued that the concept of an infinite universe might be an illusion born of our equation's simplicity.
Meanwhile, theoretical cosmology turned toward the beginning again. If the Big Bang was not a singular explosion, but a transition, what preceded it? Quantum cosmologists explored the idea that time itself could be finite, yet unbounded. That before the Big Bang, there was not nothing, but a different phase of space-time. In the Hartle-Hawking model, the universe's wave function smooths into timelessness, erasing the very concept of before. Penrose envisioned successive eons, each universe expanding until its contents lose all distinction, then rebirthing into another through a conformal mapping. Lindy's chaotic inflation suggested an endless fractal of bubbles, each Big Bang birthing another in a self-reproducing tree of universes. In these visions, there is no ultimate boundary, only recursion. Quantum experiments on Earth began to hint at the limits of space's continuity. When two particles become entangled across distance, they behave as one system regardless of separation, suggesting that the fabric of space is secondary to information itself. If information links can transcend spatial distance, then the notion of end loses meaning. What appears separated may be fundamentally united. The holographic principle extends this further. Perhaps the entire volume of our universe is encoded on a distant surface, and what we perceive as depth is an unfolding of that code. If so, the farthest galaxy and the closest atom are entries on the same cosmic ledger. At the practical frontier, engineers prepared instruments capable of peering almost to the birth of the first stars. The James Webb Space Telescope unfurled its golden petals in the cold of deep space, capturing galaxies whose light began its journey over 13 billion years ago. Some appeared too massive, too mature for their epoch, challenging models of formation. Perhaps our understanding of time's flow in those early moments is incomplete. Perhaps the fabric of space behaved differently under extreme density. Each anomaly became a new riddle, and each riddle nudged us closer to admitting that end may be a human category, not a cosmic one. Philosophers returned to the conversation. Some argued that asking whether space ends presupposes that space is a thing, when it might instead be a relation, a network of potential interactions. In relational ontology, there is no space without matter, no emptiness without the possibility of event. Others, following phenomenology, suggested that the sense of infinity is built into consciousness itself, that our awareness projects boundlessness onto the world. Thus, the edge of the universe might coincide with the edge of perception. Yet even these abstractions draw strength from the data. Every new image from a telescope becomes a metaphor as much as a measurement. The cultural imagination, nourished by science, began to populate the void with stories again. Science fiction reclaimed the ancient question in new guises: wormholes as shortcuts through curved space, hyperspace as a neighboring dimension, the multiverse as a stage for moral and existential experiment. Each narrative, beneath its adventure, asks the same thing humanity has always asked: if there is an edge, what lies beyond it? And if there is none, what does it mean to travel forever? The difference now is that our myths orbit equations, and our equations are stranger than myths ever were.
In classrooms, children trace the timeline of the universe on paper that runs off the desk. In observatories, researchers trace spectral lines that reveal elements older than the Milky Way. In accelerators, protons collide to recreate conditions a trillionth of a second after the Big Bang. Every act of measurement extends the dialogue between ignorance and curiosity. The universe does not answer in words. It answers in background noise, in faint photons, in statistical patterns. From those whispers, we build narratives, temporary, luminous, doomed to revision, but they carry the rhythm of continuity, the sense that the cosmos is not a riddle to be solved, but a conversation without punctuation. And still, amid equations and detectors, the human experience of the night sky remains unchanged. A person standing alone under the Milky Way feels the same vertigo that haunted the shepherd, the philosopher, the astronaut. The constellations, once gods and heroes, now mark spiral arms and nebular nurseries, but their emotional gravity endures. To look upward is to fall outward endlessly. The universe, whether infinite or closed, returns that gaze without judgment, offering neither beginning nor end, only motion. Across the decades that followed, the universe itself became a laboratory for time. Astronomers tracked the cosmic expansion not only across space, but across history, measuring the redshift of galaxies born when the cosmos was a fraction of its present age. The story they uncovered was less a straight line than a symphony of epochs. The radiation era, when light dominated; the matter era, when gravity sculpted clouds into stars; the dark energy era, our own, when expansion outpaced cohesion. Space was not simply growing, it was evolving, its properties changing as new forces took command. In the language of physics, the metric that defines distance is itself a dynamic participant in the cosmic play. What we call space today may not resemble the space of tomorrow, any more than the early universe resembles the calm void between galaxies now. In subterranean caverns beneath the Alps, detectors filled with liquid xenon waited for particles of dark matter to whisper through. None have spoken yet, but the silence is instructive. It tells us that whatever fills the majority of the cosmos interacts only through gravity, shaping galaxies while eluding every instrument built to catch it. If these particles are ever found, they will redefine our concept of emptiness. If they are never found, we may be forced to abandon the idea of matter altogether and treat gravity as geometry's shadow. Either path erodes the notion of boundaries. The universe ceases to be a collection of objects in space and becomes space itself in motion. Parallel to this, quantum cosmology confronts a strange symmetry. The equations governing the universe's expansion are reversible. Run them backward, and they converge to a beginning. Forward, they predict an endless stretching. Yet in the deepest mathematics, beginning and end merge. In some models, the far future of infinite dilution is mathematically identical to the Big Bang. The dying universe and the newborn one are the same equation viewed from opposite directions. If that symmetry holds, then space has no terminal boundary, only phases, each universe blooming from the ashes of its predecessor, like cosmic spring returning after winter.
Technological eyes reached further still. Interferometers linked telescopes across continents into a single aperture the size of Earth, resolving the silhouette of a black hole horizon in the galaxy M87. The image, a ring of fire surrounding darkness, became an icon of the century. It showed that Einstein's geometry, written 100 years earlier in chalk, still governs the most extreme realities. Yet it also revealed how near the limits we have come. Beyond that horizon, our equations falter. Whether space ends there or transforms into something unrecognizable remains the most intimate mystery, a boundary not of distance but of comprehension. New missions prepared to launch. The Euclid satellite to chart dark energy's fingerprints. The Nantes Grace Roman telescope to survey billions of galaxies. pulsar arrays to detect gravitational waves from supermassive black hole binaries. Each project expands the scale of observation by orders of magnitude, but none promises an edge. Instead, they promise texture, ripples, voids, filaments, subtler patterns in an apparently endless fabric. The scientific enterprise has become less a quest for limits than an art of listening to continuity. Meanwhile, theoretical frontiers turn speculative again, echoing the mysticism of earlier ages. Some physicists proposed that our universe exists within a higher dimensional bubble, colliding occasionally with others, events that could leave bruises in the cosmic microwave background. Others imagined that the constants of nature vary from one region to another, so that the laws we consider fundamental are local dialects in an infinite linguistic field. In this landscape of possibilities, space does not end, but differentiates, branching like a tree, whose roots and leaves occupy the same infinite soil. Amid these abstractions, practical voyages continued. Robotic explorers mapped the icy moons of Jupiter and Saturn, where subsurface oceans hint at biology waiting in darkness. The boundary between astronomy and biology blurred. Cosmology and chemistry shook hands. Each molecule of water beneath Europa's crust, each amino acid found in interstellar dust, spoke of continuity across scales. If life arises wherever conditions permit, then the notion of an edge to the living cosmos becomes untenable. The universe reproduces complexity as naturally as it forms stars. In cultural memory, our picture of space transformed from blackness to ecology. Early astronomers gazed into emptiness. Their successors see structure in every wavelength. Infrared images reveal webs of dust birthing suns. X-rays expose the violence of clusters colliding. The void is crowded with process. Even intergalactic space, once thought sterile, glows faintly with background radiation and scattered atoms. The old 19th century dream of ether, dismissed and ridiculed, returns, not as substance, but as field. The quantum vacuum, seething with virtual excitations. The old term empty space survives only as a linguistic fossil. Philosophical reflection followed. If space is filled with fluctuations, and if observation collapses possibility into actuality, then every measurement participates in the creation of locality. Space, in that sense, is a product of interaction, not a pre-existing stage. The universe is relational all the way down. This echoes ancient intuitions, the Stoics' pneuma, the Indian akasha, the Chinese qi, all conceived of space as living breath. What physics calls quantum field, they called spirit, and the difference may be smaller than either side imagined.
At the same time, cosmologists faced a practical dilemma. The accelerating expansion ensures that most galaxies will eventually recede beyond our light horizon. Trillions of years from now, only the local group, Milky Way, Andromeda, their companions, will remain visible. Future astronomers, born in that far epoch, may never guess that other galaxies once existed. To them, the universe will appear static and small, the echo of today's observations lost beyond reach. Thus, the concept of end acquires a temporal dimension, not the edge of space, but the edge of memory. The infinite can hide itself behind the curtain of time. Even within our lifetime, horizons play tricks. The cosmic background radiation, stretched by expansion, will one day redshift beyond detectability. The very evidence of the Big Bang will fade into infrared oblivion. At that point, the universe will seem eternal again, looping back to the ignorance of antiquity. Perhaps this is the natural rhythm of knowledge. Understanding expands until it dissolves in its own scale, and the question, does space end, must be asked anew by civilizations yet unborn. Amid these perspectives, the smallest experiments acquire cosmic weight. When quantum entanglement is demonstrated across kilometers of optical fiber, it reenacts on Earth the same non-locality that may underpin the universe. When timekeeping achieves accuracies of a billionth of a second, the difference in gravitational potential between floor and ceiling becomes measurable. Space proves elastic even in a room. Infinity begins in centimeters. Beyond science, the human response remains emotional. Each image from a distant probe, a blue marble, a pale dot, compresses the incomprehensible into something we can feel. Carl Sagan's phrase, "a mote of dust suspended in a sunbeam," carries more epistemology than equations. It teaches that scale is moral as well as physical. The absence of an edge does not diminish us. It invites us to recognize participation rather than position. The ancient terror of falling into nothing gives way to belonging within everything. Yet curiosity refuses rest. Theorists explore the notion of simulation, asking whether the universe's discreteness could betray a computational substrate. If the cosmos were digital, space would indeed have limits, pixelated boundaries defined by fundamental bits. But even then, the higher-order system running the simulation would require its own arena, and the regress begins anew. Infinity, expelled through one door, returns through another. The question endures because the act of asking recreates the concept of boundary. To inquire is to stand somewhere and point outward. As we refine our instruments, we approach the Planck epoch, that unfathomable moment 10 to the minus 43rd seconds after the Big Bang, when quantum gravity ruled. All extrapolation stops there, not because the universe ends, but because our mathematics does. The equations blow apart like overloaded stars, scattering infinities that no renormalization can tame. Physicists dream of a theory that will cross that threshold, perhaps a quantum version of space-time topology, perhaps something entirely unforeseen. When that day comes, the boundary between before and after, inside and outside, may vanish altogether.
Even now, clues arise from unexpected directions. The discovery of cosmic neutrino backgrounds, the detection of primordial gravitational waves, or the mapping of polarization patterns in the microwave sky, all promise hints about what space was before space. Each experiment pushes the frontier not outward, but backward, toward the origin where distance itself was undefined. There, in that pre-spatial regime, our language fails. To speak of an end of space becomes as meaningless as speaking of the edge of a melody. Civilization itself adjusts to these scales. Data archives on lunar orbits and Martian soil will outlast nations. Spacecraft carry messages intended for epochs when the constellations themselves have changed. Our species, once confined to valleys and rivers, now measures in parsecs and gigayears. The mental horizon expands with the physical one. Even if humanity perishes, the traces we send, the radio waves, the faint imprints of our presence will wander indefinitely, redshifting into the background, merging with the cosmic murmur that began long before us. And still, on clear nights, observatories open their domes to the same silence that greeted the first astronomers of Babylon. The instruments have changed, the wonder has not. Each photon that lands on a detector has crossed eons of expansion, navigated gravitational tides, and survived collisions with intergalactic dust to deliver its single bit of information that somewhere, something shines. We piece those bits together into a portrait of the universe, aware that the portrait is partial, aware that completeness is impossible. Perhaps that impossibility is the true condition of beauty. The question, whispered across millennia, from the myths of creation to the mathematics of relativity, has never truly sought an answer. It has sought continuity, a way to link the finite mind to the infinite context it inhabits. Whether space ends or not, we stand at its threshold every moment, bounded by perception, yet open to imagination. The shepherd, the philosopher, the physicist, the child, they all lift their eyes and meet the same mystery, one that recedes as it reveals, that deepens as it clarifies. The night sky remains our oldest mirror, and in its depth, we find both the measure of our smallness and the proof of our participation.